There is a telescope in southern New Mexico that fires a laser at the moon, not as a demonstration, as a measurement repeated for decades. The pulse leaves the mirror, crosses roughly 384,000 kilometers of vacuum, and hits a panel of glass prisms about the size of a briefcase, sitting in lunar dust since 1969. Then it comes back. The round trip takes about 2.5 seconds. Out of every 100,000 trillion photons they send, they get back around 1, sometimes none. The operators time the return to a few trillionths of a second, and from that, they get the distance to the moon to within a millimeter. They have been doing this since the Apollo astronauts left the first reflector, through 5 decades, 3 American presidencies worth of funding fights, and the deaths of most of the men who put the target there. And every year, the number they get back is slightly larger than the year before. Not by much, by a fraction of the width of a pencil line. But it is always larger. It is never smaller. And 50 years of it adds up to a distance you could walk in a couple of minutes. The moon is leaving. 3.8 centimeters a year, about the rate your fingernails grow. It is the most precisely measured fact about our nearest neighbor. And if you take that number and run it backwards through time, it produces a result that is flatly, provably impossible. Here is the impossible part. Take 3.8 centimeters a year, reverse it, win the moon back in along its orbit year by year. Do the arithmetic, and about 1.5 billion years ago, the moon was sitting on Earth's surface, not close, touching, which cannot be true because we have lunar rock in laboratories, and it is more than 4 billion years old. The moon existed for 3 billion years before the date at which our best measurement says it should have been in contact with us. That is not a rounding error. It is not a small discrepancy at the edge of the data, the kind you resolve by tightening an instrument or adding a decimal place. The most precise number in the field, applied honestly, gives an answer that is wrong by billions of years. And nobody is hiding it. It is in the textbooks. It has been in the textbooks for over a century, sitting there as a known, unresolved oddity that most people never hear about because it does not fit into a single sentence. So there are 3 things worth the next 20 minutes. Why the number produces that result. What the rocks say happened instead, and they do have a record. And what the resolution tells you about the sky you are actually standing under, including a date on the calendar, after which nobody on this planet will ever see a total solar eclipse again. Start with how we know. In July 1969, Buzz Aldrin carried a flat panel out of the lunar module and set it on the surface of the Sea of Tranquility. It had no power supply, no moving parts, and no way to fail. It was 100 corner cube prisms, glass cut so that any light entering it leaves along the exact path it came in on, regardless of the angle. You have one on the back of your bicycle. Apollo 14 left another. Apollo 15 left a bigger one. 300 prisms. 2 Soviet rovers carried French-built arrays and left them as well. 5 targets still there, still working, more than 50 years later. The technique is simple to describe and brutal to execute. Fire a pulse. Wait. Catch what comes back. Multiply the round-trip time by the speed of light. Have it, and you have the distance. The difficulty is in the numbers. By the time the beam reaches the moon, it has spread to a few kilometers across, so almost none of it hits the target. What does return is spread out again on the way home, until the telescope catches a photon here and a photon there, buried in noise from ordinary moonlight. The strongest facility currently doing this work, at Apache Point in New Mexico, gets the Earth-Moon distance to about a millimeter. A millimeter across 250,000 miles, using mirrors that were placed by hand by men who are now mostly dead. That is where 3.8 centimeters comes from. It is not modeled. It is not inferred. It is measured over and over for 50 years. Now, why it happens at all? The moon pulls on Earth, not evenly. The near side of the planet feels a stronger pull than the far side, so the whole planet gets stretched slightly along the Earth-Moon line. The oceans, being liquid, respond most. That stretch is the tide. If Earth did not rotate, the bulge would sit permanently under the moon, and nothing else would happen. But Earth does rotate, and it rotates far faster than the moon orbits, once a day against once a month. So the planet drags the bulge forward, out from under the moon, by a few degrees. It never catches up, and it never settles. And that misalignment is the entire story. The bulge is mass. Mass has gravity. Because it sits slightly ahead of the moon rather than directly beneath it, it pulls the moon forward along its orbit, a constant, gentle tug in the direction of travel. Add energy to an orbit, and the orbit widens. So the moon climbs. Meanwhile, the moon pulls back on that bulge, dragging against Earth's rotation, and the planet slows down. You can see the misalignment without any instruments at all. High tide does not arrive when the moon is overhead. It arrives afterwards. The exact delay depends on where you are standing and the shape of the coast, but the lag is real, and it has been in tide tables for centuries. That lag is the bulge running ahead. The books call it tidal friction, which makes it sound like something wearing out. It is closer to a transaction. Angular momentum leaves Earth's spin and arrives in the moon's orbit. The total stays the same. We are, very slowly, paying the moon to leave, and the currency is the length of our own day. So the mechanism is understood, the measurement is excellent, and the arithmetic is trivial, which is exactly what makes the result so awkward. Run it backwards at the observed rate, and the moon reaches Earth's surface about 1.5 billion years ago. Astronomers have known this since the 19th century. George Darwin, son of the naturalist, worked out the essentials of it before anyone had radiometric dating to argue with. For a while, that number was taken seriously as the age of the moon, and Darwin built an entire theory on it, that the moon had been flung out of a fast-spinning early Earth, and the 1.5 billion year mark was the moment of separation. It was elegant. It explained the recession, and it was wrong. Then geology arrived with rocks, and the rocks said 4.5 billion years, and the two answers have been sitting side by side ever since, incompatible. There are only 3 ways out. Either the measurement is wrong, it isn't, and it has been checked to a millimeter by 5 independent installations, or the mechanism is wrong, it isn't, we can watch it operating, or the assumption underneath the arithmetic is wrong, and it is. The assumption is that the rate has always been what it is now. That is the mistake, and correcting it does not just fix the timeline, it changes what kind of thing the moon's departure actually is. The rocks keep a record, and it is more detailed than you would expect. Start with a clam. In 2020, a team ran a laser across the fossil shell of Turretes sanchezi, a rudist bivalve that lived in a warm, shallow sea about 70 million years ago, near the end of the age of dinosaurs. Shells like this grow in daily layers. the way trees grow rings, a band for each day, thicker in the light, thinner in the dark, with a seasonal cycle laid on top. Count the daily bands inside one seasonal cycle, and you have counted the days in a year 70 million years ago. The answer came back 372, not 365. The year was the same length that is set by Earth's orbit around the Sun, which the Moon does not touch. So if there were more days in it, each day was shorter, about 23.5 hours. Earth was spinning faster. Go further back, and the same trick works on different materials. Tidal rhythmites are sediments laid down in estuaries, where each tide leaves a layer, and the layers thicken and thin with the fortnightly cycle of spring and neap tides. Read them carefully, and you can recover not just the length of the day but the length of the month, which tells you the distance to the Moon. Corals, stromatolites, banded iron formations, different rocks, different eras, same method. The picture they produce is consistent, and it does not match the extrapolation. Averaged over the last 620 million years, the Moon has been receding at roughly 2.17 centimeters a year, barely more than half of what the lasers in New Mexico measure today. The record does not say the number is wrong. It says the number is unusual. Here is the resolution, and it is not about the Moon at all. The rate at which the Moon retreats is set by how much energy the tides dissipate, and that depends almost entirely on the shape of Earth's oceans, how wide the basins are, how deep, how the water sloshes when you push it. Every basin has a natural rhythm, a period at which water wants to swing back and forth. When the tidal forcing happens to line up with that natural rhythm, the response is amplified enormously. It is the same reason a child on a swing goes higher when you push at the right moment and barely moves when you push at the wrong one. Get the geometry right, and a modest push produces an enormous swing. Get it wrong, and the same push does almost nothing. The North Atlantic, as it is shaped right now, is close to resonance with the semi-diurnal tide, the twice-daily rhythm that dominates most coastlines, close enough that an outsized share of the entire planet's tidal dissipation happens in that one ocean. But ocean basins are not permanent. Continents move. The Atlantic did not exist 200 million years ago. It opened and widened, and it is still widening, and its resonant period has been drifting the entire time. So the Moon's retreat is not a constant. It is a curve, and the curve is controlled by plate tectonics, which means something slightly unsettling about the position we are observing from. 3.8 centimeters a year is not the Moon's normal speed of departure. It is close to a maximum. We are living in one of the periods when the oceans are shaped to bleed energy out of the Earth-Moon system as efficiently as they ever have. There have been long stretches when the rate was far lower, when the continents were assembled into a single mass, and the world ocean was a wide, deep, badly tuned basin that swallowed the tide without amplifying it. During those stretches, the Moon barely moved. Then the supercontinent broke. New basins opened. Some of them came into tune, and the retreat accelerated again. The correct picture is not a steady drift. It is a sequence of long, quiet periods punctuated by episodes of rapid recession, driven by where the continents happen to be. And the driver is not astronomical at all. It is geological. The Moon's orbit is being shaped over hundreds of millions of years by the slow rearrangement of rock on a planet 250,000 miles away from it. and that resolves the impossible number completely. Run the moon backwards using an average that respects those quiet periods, rather than today's peak rate, and it does not touch Earth 1.5 billion years ago. It stays out where the rocks say it was. The contradiction was never in the data. It was in the assumption that the present is typical, which is worth holding on to because it is the single most common error in reading any long record, assuming that the moment you happen to be measuring from is the normal one. If you have stayed this long, this is what the channel does. One subject, taken all the way to the bottom. Subscribing costs nothing, and it is the only signal that tells me to keep making them. Now, the other half of the transaction. The moon gains orbit. Earth loses spin, and that is measurable too, on instruments far more ordinary than a lunar laser. The day is getting longer by somewhere between 1 and 2 milliseconds per century. That is not a figure you will ever feel. It is a figure that atomic clocks and ancient eclipse records agree on. And the eclipse records are the interesting part because they work backwards from geometry. A Babylonian tablet records a total eclipse over a named city on a named date. We can calculate exactly where the shadow fell, given a constant rotation rate. The calculated position is wrong by hundreds of kilometers. The only way to reconcile the tablet with the sky is to accept that Earth was turning slightly faster then, and the accumulated difference over 2,500 years is a matter of hours. That is why leap seconds exist, not because clocks drift, but because the planet does. Every few years, someone has to decide to add one, so that atomic time and the actual turning of the Earth do not slide apart. It is one of the very few places where this whole process reaches into ordinary life, and it does so as an administrative footnote that almost nobody notices. Stretch the same effect across geological time and the numbers become strange. 70 million years ago, 23.5-hour days. 600 million years ago, closer to 22. Go back to the beginning, to the era just after the moon formed, and the estimates run down to 5 or 6 hours. A day that began and ended before you finished a night's sleep, under a moon that filled a large part of the sky. Which brings us to the thing we are going to lose. The sun is about 400 times wider than the moon. It also happens to sit about 400 times further away. Those two numbers have no reason to match. There is no physical law connecting the size of a star to the size of a rock that formed from debris after a collision. It is a coincidence, and it is the reason a total solar eclipse looks the way it does. The moon covers the sun's disk almost exactly, leaving the corona visible around a black center. A little larger and the corona would be hidden. A little smaller and it would be drowned in direct light. We are on a planet where the geometry lands, for the moment, precisely in the narrow window that makes the sight possible. But the moon is retreating, and a retreating moon looks smaller. It is already too small at the far end of its orbit. That is what an annular eclipse is, when a ring of sunlight stays visible all the way around because the moon is too far away to cover the disk. Those are becoming more common. Totals are becoming rarer. Extend the trend, and there is a point where the moon is too distant to fully cover the sun from anywhere on Earth at any point in its orbit, ever again. The usual estimate puts that somewhere around 600 million years from now, though the number carries real uncertainty because the continents have to move first and we cannot say where they will be. there will be a last one, a final total solar eclipse, with a final path of totality falling across some coastline that does not have a name yet, and then a sky that never does that again. Go back to the telescope in New Mexico. Tonight, if the sky is clear, it will fire again. The pulse will cross the gap, strike a panel of prisms that has been sitting in the dust since before most people alive today were born, and come back 2.5 seconds later, carrying a number. And the number will be a fraction of a millimeter larger than the last one. That is the whole story. Not a catastrophe, not a countdown, just a quantity that increases and cannot be made to decrease. What stays with me is not the leaving. 600 million years is not a human problem, and nothing about this requires anyone to worry. It is the coincidence we happen to be standing inside. The moon is the right size, at the right distance, in the right era for a species with eyes to look up and see a black disk ringed in fire. It was not always true. It will not stay true. We arrived during the window, and we are the only ones who will ever have known it was a window at all, which raises a question about what else is disappearing on a timescale we do not notice. And one of them is not 600 million years away. It is happening now, in a single human lifetime. Roughly 80% of people alive today cannot see the Milky Way from where they live. Not because it moved, because we turned the lights on. That is the next one.